two people have committed a crime together and they're being arrested, and now they're held in custody separately, so they cannot communicate with each other. Okay. So from their point of view, their actions are simultaneous, because I have no idea if the other party has made a decision yet or not, so I don't know what they've done. This is as good as moving at the same time. Okay, so we have two prisoners. They're on trial for some crime, and each of them has two choices. They can either confess or they can remain silent. Now, the interesting thing is that if they both remain silent, it would be really hard for the police to prove the main crime. So they would each go to prison for a short amount of time, let's say for 2 years each. Okay. If they both confess, that's horrible. Both of them will go to jail for 4 years. But now, if one of them confesses and one of them stays silent, the police will reward the one who confessed. So the one who confesses will go to jail for, let's say, 1 year, and the other one will go to jail for 5 years. Okay. So we can show this as a sort of a cost matrix. So I can have something like this. We can have a matrix. This is, I want to draw a 2x2 matrix in this system. Hopefully we can. Okay. Yeah. So I have two people. Let's call them player 1 and player 2. So let's say this is player 1, this is player 2. And each of them has two options, either to confess or to remain silent. Okay. Now, the cost that they're going to have, which is like the amount of time they're going to spend in jail, is going to be dependent on both parties' choices. So if they both confess, they're both going to get a cost of 4. Okay. If player 1 remains silent, but player 2 confesses, then player 1 will go to jail for 5 years and player 2 for only 1 year. Okay. This one is the opposite case. Player 2 remains silent, player 1 confesses. So player 1 is going to get 1 year and player 2 is going to get 5 years. And if they're both silent, they're each going to get 2 years. So this is how we usually show a one-shot game. We show it by a matrix, basically. And one player chooses the row, the other player chooses the column, and then the entries give you the payoffs for the 2 players. It's actually not really one matrix, it's 2 matrices, right? So I have one matrix for player 1, the payoffs of player 1, and I have another matrix, which is the payoffs of player 2. Okay. Now, look at this matrix here, and suppose that both players are rational, and by rational, I mean that they only care about their own cost or their own payoff. If it's a cost matrix, we say that they want to minimize their own cost. If it's a payoff matrix, I want to say that they want to maximize their own payoff. In this case, it's a cost matrix. So both parties want to minimize their total cost, their own cost, and they don't care about the other. Okay. So here's the thing. If the two players cooperated with each other, they could just decide to remain silent, and they would each get a prison sentence or a cost of 2 for a total cost of 4, which is actually the optimal solution here. Like if you want to minimize the total amount of time that they both spend in prison, and like the sum of the times that they spend, this is the best solution. But now let's analyze it from the point of view of player 1. Let's say I'm player 1 and I'm selfish. I only care about my own benefits. So here's the thing. I don't know what player 2 is going to do. Player 2 is either going to confess or remain silent. So I don't know which column of this game I'm going to end up. Okay. Now, if player 2 is going to confess, what is the best thing I can do if I knew that player 2 was going to confess? Yeah, the best thing to do is to also confess, because if I remain silent, I get 5 years. If I confess, I get 4 years. So if I know that player 2 confesses, the best thing to do is to confess. Now, let's say I know that player 2 remains silent. What is the best thing I can do as player 1? Confess. Right? Because if I confess, I get 1 year. If I remain silent, I'll get 2 years. So a rational analysis from the point of view of player 1 says that I don't care what player 2 is doing. I have to confess, because in any other case, I'm going to get a higher pay, a higher cost. Sorry. So player 1 does this analysis and confesses. But player 2 is also rational, and this matrix is symmetric. So player 2 does the exact same analysis, and player 2 confesses as well. And we end up in this case where they go for 8 years, like a total cost of 8 years in jail, which is really much worse than this one. Okay. So let's just formalize this concept and let's see what it is that we found here. So first of all, I want to say that each of my players has a set of strategies. In this case, each of them had exactly 2 strategies, either to confess or remain silent. But in a general game, and I shouldn't necessarily have 2 players, I might have n players. So a one-shot game with n players consists of these things. Consists of, well, I'm going to have a set of strategies for each player. So a set Si of strategies for player I. Okay, so the idea is that player I chooses one of the strategies in Si. And I use big S for sets, and I will use small s for a particular strategy. Okay, but what else do I need? I need some cost function or some payoff function. I usually prefer to work with payoff functions. So I say that for every player, I also have a payoff function. Let's call it UI. This is the income or payoff of player I. And what is the type of this function? Well, it's going to be from S1 times S2, so on to Sn to R. And the idea here is that the payoff that a player gets is not only dependent on their own choice, their own strategy, it's dependent on everyone's strategies. So if you give me the n strategies that were played by all the n players, I can tell you what the payoff is for this particular player UI. Okay, and of course I have this for every player. For every player, I have a set Si of strategies, and I have a payoff function UI. Si does not have to be finite, but honestly, I mean, we will probably see one example of strategies being infinite, but in most cases, we're working with finite games in the sense that they have finite strategies. So basically, in this case, my set S1 is these 2 strategies, confess or stay silent. My set S2 is the same. And then I have a payoff function for player 1, which are these numbers. Well, actually, these were costs. So you have to just multiply by -1, and then it would be payoffs. And then I have payoffs for player 2, which are just. And my assumption is that everyone wants to maximize their own payoff. They don't collaborate with anyone else. They don't care about anyone else. They just want to maximize their own payoff. Okay. So every player is rational. By the way, this is the definition of rationality in this field. Rational means that they're only interested in maximizing their own payoff. maximizing UI, let's say. Every player I is rational and only interested in maximizing UI of. Okay. But actually, before even defining rationality, I could do something else here. I could say, what's an outcome of the game? So whenever I play this game, every player chooses a strategy and they all do it at the same time. Now, when I say at the same time, I mean from the point of view of the players. So I mean that whenever a player is choosing a strategy, they don't know anything about other players' choices. It doesn't have to really be at the same time, right? So each player, let's say I, chooses a strategy. I'm going to call this small si, which is in the set big si, one of the strategies available to player I. And the outcome of the game is basically S, which is S1, S2, so on to Sn. So the outcome of the game is just the sequence of all the strategies that people have chosen. And now we go back to rationality. Why is the I dots there? What I itself is? Okay. So every player I is rational, which means only interested in maximizing UI of S. Okay. I'm also going to define a small notation that I'm going to use later. So when I write SI, this means the iced component of S, but it also means the strategy that was chosen by player. Sometimes I want to talk about the strategies chosen by the other players. And I show that with S minus I. Okay, so this is just S1, S2 to Si minus 1, and then Si plus 1, so on to Sn. So all the entries except for the ice entry. And then sometimes I also really make the notation worse. And I write things like this, Si, S minus I. And what I mean here is that you should somehow know that I'm putting this in the correct position, right? For example, if I want to change only the strategy of player I to something else, I would write something like this, S prime I, S minus I. And what I mean here is that the strategy of every other player is the same, but I've changed the strategy of player I to some S prime I. Okay. Yeah, apologies for that, but this is just the way things are done. Okay. What we defined here was actually the concept of a dominant strategy. So a dominant strategy for player I is a strategy that would give this player the maximum payoff no matter what the other players are doing. Okay. So let's write it like this. Let's formalize it. I say a strategy Si in the set of strategies available to player I is dominant if for every strategy that I can have for the other players. So for every S minus I, and for every other strategy that I can have for the current player. So every S prime I. The payoff of player I, if this player plays Si and the rest play S minus I, is at least as much as if this player plays S prime I and everyone else plays. Okay. So no matter what the other players are playing, it's best for me as player I to play Si. That's what a dominant strategy is. Okay. So going back to prisoner's dilemma, confessing is a dominant strategy. It doesn't matter what the other people are doing. if I confess, I'm going to definitely get the best possible. Okay. Now, the thing about dominant strategies is that if they exist, a rational player will always take them. Right? Because as a rational player, I just care about maximizing my payoff. And all this is saying is that you can just ignore whatever the other players are playing. If you just play SI, you're always going to get the maximum. Okay. But in a lot of the games, we don't have a dominant strategy. Actually, before that, I want to give you another example that shows that when we have dominant strategies, usually the game is really badly designed. So this is the pollution game. The idea is this. So you know that there's been a climate summit recently, and like the different countries are trying to reach an agreement about their CO2 emissions and so on. This game is actually modeling something very similar. The idea is this. Let's say we have n players and countries, and each one of them has the option of either polluting or not polluting some resource. Okay, so they have the option of either controlling their CO2 emissions or not. Okay, and the idea is this: instead of writing the matrix and the UIs and so on, I just say that if a country does not pollute, so stops pollution, this is going to cost, let's say something, it's costs 5. I'm just giving it a number. Okay. If a country pollutes, it doesn't cost them anything. So if a country pollutes, they don't lose anything. But every country is going to get a cost of 1. Okay, so if a country pollutes, every country loses 1. So generally, the idea is that if I have K countries that are polluting, so with K pollutants, I have this. The cost for everyone else, everyone who's not polluting, is going to be K plus 5. Right, because they have a cost of K from everyone else who's polluting and a cost of 5 because they're not polluting themselves. And this is everyone else. Cost for polluters is going to be just K. Okay, so this is my game. And again, I'm talking of costs here. I can talk of payoffs, just multiply it by -1, that's all. So a cost of 5 is like a payoff of -5. Now, if you're in a situation like this, the dominant strategy is to pollute. Right? Because here's the thing. Suppose I don't know what the other players are doing. We have n players. I don't know how many of them are going to pollute and how many of them are not going to. Let's say that K of the other players are going to pollute. I have a choice. I can be clean and then I will pay K plus 5. Or I can also pollute and I'll just pay K plus 1. So it's a dominant strategy to pollute. And if everyone is rational, everyone will do it. And then everyone will have a cost of n. Whereas if people or these countries just collaborate with each other and all of them stop pollution, each one of them will have only a cost of 5. Okay. Great. So don't be selfish. Yes, you have to be rational. Being rational is not good. Okay. Let me give you a game that doesn't necessarily have this kind of dominant strategy for every player. So this is actually called Battle of the Sexes. Okay. I'm just going to read it from the book. It says, consider that two players, a boy and a girl, are deciding on how to spend their evening. They both consider two possibilities, going to a baseball game or going to a softball game. The boy prefers baseball and the girl prefers softball, but they both would like to spend the evening together rather than separate. Okay, so we have the payoff matrix. And this is how the payoff matrix looks like. Should be a better way of drawing this. Anyway, so we have the boy on this side, we have the girl on this side, and let's say this is baseball, and this is softball. I actually don't even know what softball is. Yeah, I'm a boy. So, and these are the payoffs, 2, 2, 6, 5. So this is now a payoff matrix. It's not a cost matrix. Yeah. So if one of them goes to baseball and the other one goes to softball, they're both sad. They have a very small payoff. And they're less sad in this case for some reason. And yeah, if they both go to baseball, the boy has a happiness of 5, the girl has a happiness of 6. And if they both go to softball, oh, this should be the opposite. Okay. Yeah, sorry. Yeah. This is the girl. This is the boy. The boy prefers baseball. So if they go to softball, the girl will have a payoff of 6. The boy will have a payoff of 5. If they go to baseball, it's the opposite. Okay. So in this case, I don't have a dominant strategy. Why is that the case? So let's look at it from the point of view of the girl. Let's look at the first strategy, going to baseball. Is that dominant? It's great if I know the boy is also going to the baseball game. But if the boy is going to softball, I would prefer to switch to softball. Right? And you can also do this for the other cases. So there are 4 cases. You can check that none of them are dominant strategies. So what happens in a game where we don't have dominant strategies? We have rational players. They still want to maximize their own payoff, but there is no dominant strategy. If there was a dominant strategy, I could just say the player will play the dominant strategy. But now there is no such thing. So we need some sort of a compromise. We need the concept of an equilibrium. Okay. What is an equilibrium? An equilibrium is a situation such that if we are in that situation, no one wants to change. Okay. So suppose that we are in this situation. Okay. So suppose that the boy has just bought baseball tickets. Right. So the boy would not want to switch, right? Because going from here down here, the payoff goes from 6 to 2. The girl would not want to switch either, because going from here to here, the payoff will go down from 5 to 1. So this is an equilibrium state. Okay. If we somehow happen to be in this state, no one wants to change. There is another equilibrium state, and it's this one. Right? If we are here, no one wants to change, because no matter who you are, all of the neighboring states have a worse fate. But of course, not all the states are equilibrium states. For example, if you're here, of course, everyone would want to change. Right? So if you're here, probably, let's say the girl changes to baseball and we end up here, or the boy changes to softball and we end up here. Okay. So this is the definition of equilibrium. And I'm going to call this a Nash equilibrium, but actually it was not the main contribution of John Nash. We're going to see a different definition of Nash equilibrium soon, which is the main one. But basically, I want to say that if I have some outcome, when is that outcome an equilibrium? So I say an outcome as, again, I'm extending this to the case where I have more than two players. So S1, S2, so on to Sn is a Nash equilibrium or just an equilibrium. This is a really long word. If, so here's what I want to say. I want to say from the point of view of every player, it would be stupid to change my strategy, assuming that other players keep their current strategies, right? So I want to say that for every player I, and for every other strategy S prime I, the payoff that this player gets in the current situation at S, which is basically the payoff at Si, S minus I, is at least as much as what this player would get if they change. So everyone else is keeping their strategy the same, only this player is changing. Okay? And I want this to hold for all the players. So the idea is that if I propose some outcome, if I propose to everyone, hey, let's play this strategy, let's play S1 to Sn. After I propose it, no one would want to change. No one has any kind of incentive to say, no, let's play something else. Because if other people stick to it, then they will either lose or at least not gain anything. Because this might be equal. So in this case, it's like if someone else comes and proposes that we want to be in this state, the top left. Neither the boy nor the girl want to change their strategy. They want to stay where they are. Now, intuitively, especially in economics, people say that this makes a lot of sense if you have a game that is being repeated. So imagine that they're playing this game every day, and every day they're here, right? So every day, each person knows that the other person is probably going to go for baseball. So they're not going to switch their strategy because the expected payoff that they're going to get is off, right? Again, we don't care about psychology. Psychology is not a science, okay? This is math. So we have two different Nash equilibria here. This one is a Nash equilibrium, and this one is a Nash equilibrium. Okay. So we started with a very strong concept of a solution to a game, and a solution to a game is basically saying what rational players would do, which was the concept of dominant strategies. We said that if there are strategies for all the players that are dominant, everyone would play that. But then we said, well, in a lot of the games, we don't have dominant strategies, so we found a weaker notion of a solution for a game. And this is the equilibrium idea. Okay. Can I have a game that doesn't have an equilibrium? Just design a game without a Nash equilibrium. There's actually a famous game that I'm pretty sure you've all played. Rock, paper, scissors. Rock, paper, scissors doesn't have a Nash equilibrium. So let's say, let me draw the matrix for rock, paper, scissors. This is even harder to draw because it's a 3x3 matrix. Okay, assume these are all the same size, okay? Ah. I don't know why it does this. What the hell? Okay. Okay. Great. If I later find out that I could just draw a table, I would be really angry. No, there is nothing for drawing tables. Okay. So let's say we have two players, player 1 and player 2. They each have 3 possible strategies: rock, paper, scissors. Rock, paper, scissors. If player 1 plays rock and player 2 plays rock, they both get a payoff of 0. If player 1 plays rock and player 2 plays paper, this is the payoff. Player 2 is winning. And if it's rock and player 2 is scissors, then player 1 will win. Okay. This is going to be painful. I have to fill out all of this. So if player 1 is doing paper and player 2 is doing rock, it's this. This one is 0. This one is -1. It's scissors and rock is -1, 1. Scissors and paper is 1, -1. Scissors and scissors is 0. Okay. So this is my payoff matrix. And again, whenever I'm writing these matrices, I have to be careful to tell you whether it's a payoff matrix or a cost matrix, but this is a payoff matrix. Okay. Why don't I have a Nash equilibrium? Why is none of these 9 states or 9 outcomes a Nash equilibrium? So no matter where I am here, there's at least one person who can improve. Right? If I'm in a state where, let's say I'm on the diagonal, where they're tying, then actually both of them can improve. So for example, if I'm at paper, player 1 can choose to scissors, can switch to scissors, and that would be a better strategy, they would win. Player 2 can do the same thing, go to scissors and so on. In the cases where there is a loser, the loser can decide to go to one of the cases that gives us a tie. Or actually even better than that, the loser can decide to go to a case where they win. Right? So no matter where I am, I'm never going to have the same kind of stability that I have in an equilibrium, because at least one of the two players wants to change what they're doing. Okay, so this is an example of a game without a Nash equilibrium. Actually, I have to say something here. I actually would call this a pure Nash equilibrium. You'll see why very soon. So it's a pure Nash equilibrium with this. Okay. I'm going to give you another game because I want to have a smaller game that doesn't have a Nash equilibrium. Let's say I have 2 players and they're each going to flip a coin, but they're both cheaters, so they don't actually flip the coin. They just choose heads or tails, right? And the idea is that if they choose the same thing, I'm going to say that player 1 gets some positive payoff. And if they choose different things, I'm going to say player 2 gets some positive payoff. So this is the matching pennies game. Yeah, the coins are pennies. What? Okay, whatever, I can't fix that. So again, I have player 1 on this side, player 2 on this side. They can say heads or tails. Okay. If they both say heads, player 1 wins. So player 1 gets a reward of 1, player 2 gets a cost of 1. If they both say tails, the same thing happens. Otherwise, if one of them says heads and the other one says tails, player 1 loses, let's say, $1, and player 2 gains. Again, this is a game where you don't have a pure Nash equilibrium. You can just check each of the 4 states. In each state, you have a loser, and the loser would want to change their strategy. What should we do in cases like this? We need somehow to define an even weaker notion of a solution. So again, I started with a very strong notion of solution, dominant strategies, but I saw that most games don't really give most players dominant strategies. And I mean, in the cases where I did have a dominant strategy, it was usually a stupid game with a stupid strategy. Now, then I went to pure Nash Equilibria. And the idea here was that, well, let's find something that is an equilibrium, something that is self-enforcing. At least people don't want to change. And now I'm seeing that a lot of games don't even have that. So I'm going to give my players more choice. Instead of saying that every player has to choose a strategy, I let them use probability. I want to say that each player should choose a distribution over their strategies. So I'm going to choose each one of my strategies with some probability. Okay. So this is what I call a mixed strategy. So a mixed strategy is just a mix of normal strategies, and like normal strategies are called pure strategies. Okay. So a mixed strategy, let's say for player I, well, it's going to be a probability distribution. So I'm going to just say that it's a function, let's call it delta I, from Si to the segment from 0 to 1, basically assigning a probability to every pure strategy. And I also use big delta sub I to show the set of all possible mixed strategies of player I. Okay, set of mixed strategies. So now the idea is that instead of saying I either play rock or paper or scissors, I can assign some probability. I can say with probability 0.1, it's rock, with probability 0.2, it's paper, with probability 0.7, it's scissors. What can I do? I can now define a Nash equilibrium with mixed strategies, a mixed Nash equilibrium, right? But before I do that, I have to really talk about these payoffs, because my payoffs were functions that would take some outcome of the game and tell me how much money I'm going to make as player I, right? But now I don't have just one outcome of the game because all the players are choosing their strategies randomly according to some distribution. But that's fine, because I can say, well, if I know what strategy each player has chosen, what mixed strategy each player has chosen, I can find the expected value of my payoff. And let's say that we change the definition of rational. So we say that we have all of these things. So let me just copy this again. So now I'm going to say this. I'm going to say that each player chooses a mixed strategy. Let's call this one delta I in Si. And then the outcome is S of this, where each Si is sampled according to delta I. And I write it like this. Right. So each one of the players is just choosing the probabilities assigned to their strategies. And then we're all going to play at the same time. We're all going to generate our random numbers at the same time, pick our strategies based on that. And then there's going to be an outcome. Now, every player is rational, so they're interested not in maximizing their payoff, but in maximizing their expected payoff, right? And again, this is expectation when every Si is sampled according to delta I. Okay, great. So now based on this, I can take my concept of pure Nash equilibrium and I can extend it. I can say what is a mixed Nash equilibrium, or actually this is what people usually just call Nash equilibrium. So a mixed Nash equilibrium is just going to be this. We say a sequence of mixed strategies. also, usually I call it a strategy profile. So whenever I say a strategy profile, I mean a strategy for each player, like a sequence of strategies, and it can be mixed strategies or pure strategies. So we say a strategy profile, let me actually use sigma this time, sigma 1, sigma 2 to sigma n. And remember, each of these strategy profiles is just a probability distribution. Sorry, each of the components of the strategy profile is a mixed strategy, which is a probability distribution. Okay, we say this is a Nash equilibrium or a mixed Nash equilibrium if, again, I want to say the exact same thing. I want to say from every player's point of view, if other players stick to their strategy, it would not make sense for me to change my strategy. Okay. So I want to say that for every player I, and for every other mixed strategy, every sigma prime I have this, the expected utility of player I, the expected payoff of player I, if player I plays sigma I and everyone else plays sigma minus I, is greater than or equal to the expected utility if player I plays sigma prime I and everyone else plays sigma minus I. And again, I do have a little bit of an abuse of notation. Because at the end, I mean, if I want to write this correctly, I should write UI of S, and I should just write in the subscript that S is sampled differently. Right, so here what I mean is that the ICE component, the ICE pure strategy is sampled according to the mixed strategy sigma I. But here, the ICE component is sampled according to the mixed strategy sigma prime. Okay, but basically it's the same idea as before. It's the idea that, well, if everyone else keeps their strategies the same, I'm not going to change my strategy. There's no incentive for me to change my strategy. Okay. Does rock, paper, scissors have a mixed Nash equilibrium? Give me a mixed Nash equilibrium. It's very intuitive, actually. So you have to give me a strategy for each side, and it's a mixed strategy. So for each side, you have to tell me what is the probability of playing rock or papers or scissors. And we want to make sure that we are in an equilibrium. We want to make sure that no one can benefit by changing their strategy. Just play randomly and uniformly, right? Like play each one with the same probability. So let's say that sigma 1, the strategy of player 1 is just a third, a third, a third, by which I mean that rock is played 1/3 of the time with probability a third, paper is played with probability a third, and scissors is also played with probability a third. And let's say that sigma 2 is also the same thing. Why is this an equilibrium? Why is this a mixed Nash equilibrium? So look at it from the point of view of player 1. If we fix the strategy of player 2, if we know that player 2 is going to play this, does it make sense to change my strategy? Does it make sense to change any of these probabilities? Look, if this is sigma 1 and this is sigma 2, my expected payoff is 0. Right, you can just figure that out, just do the calculations. But let's say I change one of the probabilities. Let's say, for example, I say I want to play rock with a higher probability. Okay, is that going to increase my probability of winning? No, because whenever I'm playing whatever I am playing, the other side is playing totally randomly, right? So if I'm playing, let's say, rock with probability X. So actually, let me do this. Let's say sigma 1 is XYZ. I'm playing rock with probability X, paper with probability Y, scissors with probability Z. What is my total payoff? So when I'm playing rock, which happens with probability X, the other player, independently of me, is playing either rock or paper or scissors, each with the same probability. So with probability a third, they're going to also play rock. So, and my reward is going to be 0. With probability a third, they're going to play scissors, and my reward is going to be 1. With probability a third, they're going to play paper, and my reward is going to be -1. My payoff is going to be -1. And then I have the same thing for Y and Z. So Y times the same thing plus Z times the same thing. So no matter what the hell I do, my expected reward is 0. Right? So yeah, I cannot change my strategy to increase my reward. Look, this is greater than or equal. Okay, I can change my strategy and get the same reward. That's fine, but I wouldn't do that because I mean, what's the incentive to change your strategy if it's not paying you anymore? But in this case, basically, it doesn't matter what my strategy is. If my opponent's strategy is uniform, I'm going to have an expected payoff of 0. But this doesn't mean that if I change my strategy, I would still be in an equilibrium. As soon as I change my strategy to something else, then my opponent would have an incentive to change their strategy, basically adapting to mine. So if I play rock more often, then they would want to play paper more often. Right? So the only case where I have an equilibrium is actually when both of them are playing uniformly like this. And here you can also find an equilibrium. And I guess here the equilibrium is also uniform as well. Now, finally, I'm going to end the session with a theorem that I'm not going to prove because Nash won a Nobel Prize for this. I don't think it's something that we can cover in 27118, but I can give you the theorem and you can understand what the theorem is. So this is the theorem of Nash. By the way, if you have watched the movie, I think it was The Beautiful Mind, right? Yeah, all of it is about this theorem, basically. So the theorem of Nash is this. Any n-player game, so I should have a finite number of players in which every SI is finite. So every player, this is S, not delta. I have to be careful how I'm. So if I have a game and I have a finite number of players, and then if every player also has a finite set of pure strategies, then I have a Nash equilibrium. So any n-player game in which every SI is finite has a mixed Nash equilibrium. We can start with this concept of solution, and this is too strong. I cannot guarantee that every game will have it. Then I made it a bit weaker. I said, okay, let's say that we don't want to have a dominant strategy. We just want to be in an equilibrium. We just want to say that each person is not willing to change their strategy if the other people also stick to their strategies, right? And then we saw that this was also not enough. The next step was we're going to let them use probability. And this is somehow enough. Now, very importantly, if you have an infinite number of players, the theorem does not hold. You can actually come up with counterexamples pretty easily. If you have an infinite number of strategies for a player, the theorem does not hold. It's only for finite games. If you have a finite number of players and the strategy set of every player is finite, then you have a Nash equilibrium. Now, fun fact, we don't know how to compute phi. So it's actually one of the open problems, one of the famous open problems in computer science. We don't know if there is a polynomial time algorithm that, given a game, computes a Nash equilibrium. Now, the problem is not NP hard, because I mean, we haven't really talked about complexity classes and NP hard and so on, but basically the idea is that when you talk about NP hard problems, you're saying that it's a problem where it's hard to say whether the answer is yes or no. We have this theorem, the answer is always yes. Whenever I give you a game, it always has a mixed Nash equilibrium, but we don't know how to find one. It's not constructive. We just know that one exists.